Very good afternoon everybody. This is Dr. Vaibhav Pandit and today we are going to have a session for your doubts related to the topic titled electric field of a line charge. So this is basically the topic from our subject electromagnetic field theory, and for this subject I think this is our sixth session. So before, we are already covered with introduction to the vectors and the rectangular coordinate system, then the cylindrical coordinate system, spherical coordinate system, introduction to the vector operator del and the gradient divergence curl operation. Next to that, the Coulomb's law and electric field intensity we are well familiar from our last session here. So a background to this particular topic, as we have the electric field of a line charge comes from the Coulomb's law. So this is the first law from our chapter that deals with the behavior of the electric field. Our subject is having the two fields to study, and that study is also to be done together. So the study of electric field and then magnetic field, and both at first of all the two conditions, the static condition and then the dynamic condition. So first of all we understand all the laws and the principles of operation into the static condition, hence we call them electrostatic, and then further the magnetostatic will definitely be there. One of the line session we shall be conducting thereupon. So for electrostatics, the Coulomb's law is very fundamental law here. So we call it to be the electrostatics force law given by the Coulomb here. The situation that we had taken, that we had the consideration of the two charges into the space separated by a certain distance. So in this particular simple diagram you can see the two charges, the magnitudes of these two charges are represented by capital Q1 and capital Q2 into the measurement of unit is coulombs here, of course into the SI system of unit named by the same inventor Coulomb here. Now the position and the location of these 2 point charges, now I hope we are well practiced to provide by either rectangular coordinate system or cylindrical coordinate system or the spherical coordinate system, because here we have the reference point. So when we are dealing with the rectangular coordinate system, we expect the three axes, those are mutually perpendicular to each other, intersecting at this particular point. So I get this to be the horizontally lying y-axis, this to be the z-axis, and here x-axis, both intersecting in this particular location here. Now in such a situation, the information with respect to the force of interaction between these two charges is conveyed by the Coulomb's law. The statement we can recall. So the statement is the force between the two very small objects separated in a vacuum or a free space by a distance which is large compared to their size is proportional to the charge on each and inversely proportional to the square of the distance between them. So in this statement for the Coulomb's law, these 2 points are very important, because the force is a dependent quantity that is to be calculated here, and it can be calculated when we have the knowledge of these two things. Here we require the magnitude of the charges and what is the distance of separation between these two charges. So knowing these two quantities here, we shall be able to compute the force here. So let us have a simple illustration where we apply the Coulomb's law. So these are again the two charges, as we had a consideration of capital Q1 and capital Q2 in terms of coulombs here. Now we have these magnitudes. Now we require the distance of separation, for which a square is to be taken, and there it is inverse proportional of the force of interaction to this distance square here. So for that purpose, determining this particular vector r12 and then further finding its magnitude, we need to join the locations of this q1 and q2 to the origin, so that we obtain these two particular vectors r1 and r2, and by having the subtraction as we follow the triangle law of addition here, we will be successful to obtain this particular vector, and the magnitude of it will be the distance of separation. So whatever the information has been conveyed by the Coulomb's law statement, it is with respect to first of all magnitude only, and the direction is to be decided depending on the higher magnitude in between the two charges here. So we know that the like charges repel each other, whereas the unlike charges attract each other here. So according to the Coulomb's law, we have this particular formulation for the force. So in this formulation, as per the statement provided, the force of interaction at the second place here, it is mentioned, is directly proportional to the multiplication of the two magnitude of the charges here, Q1 and Q2, whereas it is inversely proportional to the square of the distance between them. So after removing the proportionality sign here, we get to the constant 1 upon 4 pi epsilon 0. Hence 4 pi epsilon 0 here it is in the denominator. Now along with this much of magnitude, we have information regarding direction conveyed, that it is represented here by this particular unit vector denoted small a suffix 1 2, as it is directed from position 1 to that of the position 2. Now how to get the unit vector to be substituted to complete the representation of this particular force? So here A12 can be simply obtained by dividing the vector directed from first location to the second location, expecting there it is the charge at first location exerting a force onto the second location. So that vector it will be R12 in capitals, and dividing it by the magnitude represented by the mod here, or in terms of R1 and R2 we can also represent this way. So this is the very fundamental basics. I suppose it should be clear. Then we have a very good interest and further understanding of the electric field here. Now electric field intensity also I have introduced you in the previous session. So electric field intensity can be derived by the knowledge of this force of interaction as described by the Coulomb's law here. Now in the place of Q2 charge, if we put such a test charge representing it by capital Q suffix T here, so the respective changes into the representation we have made here, and when we divide this particular formulation by Qt here, so what happens, we get a quantity again into a vector type here, that it will be the electric field intensity. So basically either you call dividing the force of interaction by the magnitude of the Qt charge, or at the second location you put 1 coulomb of charge as a test charge. So it will give you the information regarding how much strength the first charge is having. So this is what the formulation we have done, and accordingly E we obtain Q1 upon 4 pi epsilon 0 r square AR to be the unit vector here. So in general, not representing only one charge by Q1, it will be simply capital Q here. So this is what the mathematical expression, the simplest one to be for the electric field intensity. And now you can see that this is the electric field intensity produced by a point charge. Here it is the scenario here. Now our today's topic of discussion is electric field of a line charge. So definitely we shall move thereupon. So just have a recall that here we are having a source charge, that it is represented by capital Q. It is a point charge only, though I am encircling it, it is a point charge here. The location is provided by the coordinates x dash, y dash, z dash. Now because of this particular point charge, there it is into the surrounding the influence of this particular charge, whether it is positive or negative. When it is positive, another positively charged test charge will be repelled away. So let us say at this particular position, what we designate by the name capital P as a function of x, y, z. So this is a field point. So it is a point where the strength of the electric field produced by the source charge we are going to measure. Hence we shall be hereafter calling the point P to be a field point here. Now at this particular field point P, which is r distance away from the location of the source charge, that can be computed by having these vectors r dash and r here in small casing here. This is what the electric field intensity, and expecting both of the like charges here, the magnitude of the source charge, of course it will be greater than that of the test charge, so it will be directed away. So this is what the direction here we have, and this is the vector quantity electric field intensity. We have already discussed in the previous session, and the formulation just now we have revised. So E is equal to Q upon 4 pi epsilon 0 R square AR here. Now when we have the two charges into the space here, and in the surrounding there it will be the effect of both of these particular charges. So the net effect we have to compute, and accordingly we can judge the direction of the electric field intensity. Let us get this concept cleared by this particular illustration, where we have the two charges Q1 and Q2 here. So both are the source charges. They will be having equal or unlike magnitude here. In this particular case, if the two distances are the same here, so it is supposed to exert the same amount of electric force on this particular field point, that is again designated by capital P letter here. So here we shall be having the individual electric field intensity because of the first source charge exerted on the field point location, that is directed in this direction and denoted by capital E suffix 1 here. Because of Q2 charge at the field point, here it is the electric field intensity exerted having the magnitude E2, the direction is represented here. Now we have at the field point two electric field intensities. So the net effect or the total electric field intensity will be a summation of these two vectors here, E1 and E2. So magnitude can also be computed, and the direction is this way by the triangle law of addition here. Now instead of shifting from 1 to 2 charges, if we have multiple charges again, so again the same thing is to be done, that it is summation here. Mathematically the expression can be provided here. So the total electric field intensity here it is represented, so it is a function of R here, and now the summation where the index vector that it is M starting at 1 to small n here, we have the magnitude of the charge represented concerned to this M value here divided by 4 pi epsilon 0, and then here we have mod square for the difference R minus Rm into the unit vector representation here. Now we have to extend to more number of the charges, and what way? We are arranging them into a line here, into a linear fashion here. Then we will come to have electric field that it will be produced because of a line charge. Now there are different forms of the charges. In your school days also you might have been experimenting with the experiments, as like you will be having a glass rod, rubbing it onto a cotton or let us say a paper, it will be getting a charged and it will be attracting the pieces of the papers here. For the ebonite rod also there is experiment. So these are with respect to the positive and negative polarity of the charges here. So the charge can be distributed over a line, it can be distributed over a surface, it can be distributed into a volume as well. Now when we shall be having the multiple number of point charges arranged into a line, let us have the illustration with this diagram here. So let us say the first point charge is Q1, second is Q2, third is Q3, next is Q4. So this way if we go up to Qn, so it will be a series of point charges. Now we again add certain point charges into the same length. So it will be like this, the number of charges have been increased. Don't go on the size on the size of the dots I have represented here, but multiple charges here. There it is very short space, or when you have very multiple, so it will be looking like a line here. So this is what we are talking about. If onto this particular length, if we have a charge distribution, so we can call a term that it is a line charge here, and for such a line charge we are supposed to derive the electric field intensity in this particular session. So the orientation of this particular line charge can be in any direction. Suppose it may be vertically oriented line, or it may be a tilted as well. The tilted direction can also be shown like this. Now for the practice, taking into the help the coordinate systems, the first one, the simplest one, that it is the rectangular coordinate system, we can have the distribution of the charge over the axis. Let us say this is vertically oriented z axis, or this is the horizontally oriented y axis, and mutually perpendicular to both of them, that it is x axis here. So we can expect the line charge that is along z axis, y axis, or x axis. The positive and the negative ends, all of you are very clear from our previous sessions here. Now the location of the source charge is now well clear to you people, I hope so. Now while determining the electric field intensity, we should be also known to the location of a field point, that if we have, for example, I am again drawing a point charge. So because of this particular point charge into the surrounding, there it is the influence and what we call the electric field here. So at a certain location, let us say here or here or here, the strength will be different. If you go closer to the source charge, the strength will be more. If you go away from the source charge, the strength will be at weak. So we should be known to the location of the field point at which we have to derive the electric field for such a line charge. For the point charge, we know the formulation here. So if again we consider the charge distribution, here we confine to the z axis here, that is why I have shown to you into the blue color here. Now the orientations of the two axes, y axis and x axis, now you know. So I just provide a nomenclature to this: positive direction of z, positive direction of x, positive direction of y here. And onto the z axis, I expect there it is a uniform distribution of the line charge here. Now you see, whenever there it is a distribution of the charge over a line segment, we cannot measure a portion of the charge thereupon. That is why always there it is the use of another form of the charge parameter, that it is the charge density. So here it is the distribution of the charge over the length. When we divide the total magnitude of the charge by the total length here, we shall get a line charge density, and hereafter into the derivation as well into the subject, we can be denoting it with the symbol rho suffix L we can provide for representing line charge density. When it is for surface charge density, you will come to see I will be denoting it by rho suffix S, and when it is volume charge distribution, I will be denoting it by rho suffix V. The measurements units will vary. Here it will be for rho L coulombs per meter, for rho S coulombs per meter square, for rho V it will be coulombs per meter cube here. Now as we have a consideration that along the z axis we have a charge distribution, what is the location of the point? That it is at the field point location here. So the field point location can be like this. On the right hand side, I have shown to you people of the z axis in this plane here, or it may be on the left hand side. It may be on the left hand side somewhat downwards to the position of the origin. So we can have minus z while we be locating it with the help of the rectangular coordinate system here, or somewhere here. Now to derive the formulation of electric field intensity, that it is produced by such a line charge as we have considered for the z axis. For our convenience, we shall select a location onto the y axis on the positive direction here. So it will be first of all quite convenient, and by the manipulation modifications we can apply the same formula over whatever the situation that it will be asked into your problem statement here. So let us have a look onto the diagram here. So in this diagram, as I have already explained, we expect a uniform line charge distribution over the z axis here, and here it is the point P that we have taken as a field point location. This is onto the y axis. So here it is the source, and here it is the field point where electric field intensity is to be derived here. So as initially we have a knowledge of the point charge, and because of point charge the electric field intensity formulation here. So initially what we will take a differential portion from this line charge. We are not going to have consideration of first of all the entire line charge, so a small portion of it. So we shall be denoting it by dq here. So as I have explained, for the entire line charge we have a denotion of line charge density by rho L. So for the differential portion, when we have the differential length denoted by dz dash multiplied it to that of the line charge density, it will give you the magnitude of this particular differential charge that it is distributed over this much of length here. So let us consider at this point we have this much of source only, and here at this particular point P we have a field point and we have to measure the electric field intensity. So as the source is of differential charge represented dq here, we shall represent the differential electric field intensity denoted by dE here. Now as we have a knowledge of the different coordinate systems, the rectangular one, cylindrical one and the spherical one. In the rectangular we have the three references, x, y, z axis. In the cylindrical we have only one reference, that it is z axis. In the spherical we have only one reference again, that it is point here, that it is the origin intersection of the three here. So when we consider cylindrical coordinate system, so cylindrical coordinate system, we imagine a cylindrical surface that is centered at the z axis. So it will be quite convenient to have the representation of the components of the differential electric field intensity caused by the source charge like this here. So we shall be resolving into the two components, that it is the differential into the direction of rho and the direction of z that comes to the cylindrical coordinate system. So just now have a look, we have identified the location of the source, here it is the differential charge, and location of the field point, here it is denoted by capital P. Now let us derive the things here. So I shall be taking this particular illustration somewhat left hand side here. Now we shall be making the use of electric field intensity produced by the point charge. Let us say the magnitude it was for the q1 charge. So this is what the formulation here, and how to get this particular unit vector here. We have the formula, let us say from first location to the second location, hence it is denoted A12, the formulation we have taken from our previous presentation here. So a vector divided by its magnitude, we get it like this, or in terms of R1 and R2 as in the previous illustration here, we can make the use here. Now using this basic understanding, what we are going to do, we are supposed to compute the differential electric field intensity. So let us denote as in the illustration, it is by dE here. Now we expect first of all the magnitude of the source charge at the numerator. Here we are writing D to obtain this particular LHS. Now here at the magnitude, instead of writing the dq here, we shall be putting rho L into dz dash here, rho L into dz dash here. So this we have substituted in the denominator, 4 pi epsilon 0 is the same here. Now square of the distance of separation. Now here it is the distance of separation from this location to this location. Here we are representing it as r minus r dash, when r is a vector directed from the origin to the field point here. Here it is horizontally located. Just follow the symmetry what I draw with my pointer, and here it is the r dash. So from the origin, the location of, it should be a straight line, the location of the source charge here. So here we have the difference r minus r dash and the multiplication with the unit vector here. So for the unit vector, as the vector divided by its magnitude, so the combined representation for the differential electric field intensity produced because of the differential charge can be represented like this here. Now next to this, what we can have? We can have the substitution of what is the vector r, what is the vector r dash, considering the geometry that we have drawn and considered in this particular diagram here. So r, as it is directed along the y axis here, this much of length we can consider the y. So we can represent r vector by y into ay, or this is the representation into the rectangular coordinate system. When you go for cylindrical coordinate system, you have to represent it like rho into a rho. So imagine this much of length segment is of the radius of the cylinder, and this is what the shape we can draw here, and you can imagine the cylindrical surface here, that is infinite upwards and downwards here. So here it is, the r needs to be substituted in the above equation here, and r dash, this is z dash az, this is vertically oriented upwards. So along with these two vectors, when taken, the difference can be represented rho a rho minus z dash az here. So as we require the difference to be substituted in the above formula here, so we substitute it like this. Now the substitution will look like this. So in the numerator you will see rho l dz dash multiplied by, in the parenthesis we have rho a rho minus z dash az here, and in the denominator we shall be having 4 pi epsilon 0, and it will be multiplied to the square of the first bracket that it was here and the mod that it is a part of the unit vector. So combine the representation. Here we have in the parenthesis the addition of rho square with z dash square, the power in the combined, here we represent 3 by 2 here. Now after this substitution, as we see, there are the two unit vectors from the cylindrical coordinate system. One is a rho, another is az here. Now here it is for the differential electric field intensity, when we shall be extending this by integrating for the complete line charge, that it is a vertical distribution having, so with the uniform line charge density rho l here. So that time, so at what particular z level, at this level or this level, at this level, at this level, for the field point P does not matter. It is not supposed to be affecting the magnitude of electric field intensity, because what happens if at this particular position you are having the field point and a differential charge here, because of this differential charge the electric field intensity will be directed here, and at the same distance downwards, when there it is a differential charge like this, it will be the differential electric field intensity that it will be directed in this particular direction here. The addition of the two is supposed to come in this direction, that it is nothing but the a rho direction. So the latter part is supposed to get omitted here after the simplification here. So by the next step, what we do, we represent the left hand side by differential electric field intensity. The suffix is provided by rho here. The numerator on the RHS we keep rho l into dz. So this rho is different. This is the measure of length that we have taken at this particular case, and this rho l is different. Don't get confused. So this rho l is line charge density measured in coulombs per meter. This rho is simply in terms of meters. and the denominator is the same. Now, for computing the electric field intensity as a effect because of the complete line charge, we have to integrate, and as we expect the z-axis to be from minus infinity to plus infinity here, the complete electric field intensity, I don't represent a d here in the next step, so this will be E suffix rho, the component. It will be obtained by taking the integral extending from minus infinity to plus infinity over the LHS that it was in the above step here. Now, computing the integration here, the constants are first of all need to be taken outside. So we have rho L upon 4 pi epsilon 0 outside as a constant along with the multiplication of rho, and the limits of the integral will be applied to 1 upon rho square in multiplication to z dash divided by the square root of rho square plus z dash square here. So after applying the limits, you will come to see the formulation of E rho is simplified to rho L upon 2 pi epsilon 0 rho here. We have been denoting from the previous few steps E rho here. This is what just the magnitude here. The direction content is of course into the suffix here, it is rho here. So considering the direction onto the RHS also, the representation comes to capital E is equal to rho L upon 2 pi epsilon 0 rho into A rho as the unit vector. So we have completed the derivation. Just make a note here, you can outline this particular formula. This is the very important formula. Whenever you have a knowledge of the magnitude of the line charge and the location of the field point, you can use this formula, and just by putting two values here, you can obtain the answer here. The rest of these are the constants, pi 3.14 and epsilon 0. I have already taught you people that it is permittivity of the free space. The medium here for the consideration of this particular system we have considered to be either a vacuum or a free space or air here. So this is what the formula we have obtained here. Now let us have a practice of few simple problems that may come to your examination here. So let us have the first problem statement for this topic. So the problem statement is a uniform line charge of 60 nanocoulomb per meter is located along the line defined by y is equal to minus 2 and z is equal to 5 here. Next to that, we are asked to find E represented for the electric field intensity at the location P. The coordinates are provided 1, 2, 3 here. Next to that, find E at the point in the z is equal to 0 plane where the direction of E is given by 1 by 3 ay minus 2 by 3 az here. So this is your complete problem statement. So whenever you are solving the problems for electromagnetic field theory, first of all judge the situation. Where is your source charge and at what location, what I call the field point location, you have to compute the value. So from the starting sentence, there it is uniform distribution of charge over a line, hence we call it to be uniform line charge. The magnitude value is provided in terms of 16 nanocoulomb per meter. Just focus on to the measurement unit here. It is nano. Nano is just a multiplicand here, 10 raised to the power minus 9 here. Coulombs is the unit. Now coulombs is divided by meter. Meter is again another unit. So a charge, let us say magnitude divided by denoted by q here, divided by the length L here. So here it is the line charge density value provided to you in this problem statement. So let us denote it by rho suffix L, either small l or capital L. You follow the same notation throughout in your work. Now this is what the magnitude, and what is the orientation? The orientation is defined by y is equal to minus 2 and z is equal to 5. So as we have the use of y and z, let us consider the rectangular coordinate system. Let us assume that this is the vertically oriented z axis, horizontally oriented y axis, and then mutually perpendicular to the two, here we have x axis here. So let us have the 2 units markings onto the negative side. So here it is the negative side. 5 units marking onto the positive side. 1 2 3 4 and let us say 5. Here it is. So intersection of these two, we will get to this particular point. Just consider the symmetry what I draw with the help of my pointer. And now there it is a line parallel to the x-axis like this. So there it is no limit on the x. So here it is your line. So it holds the values from x minus infinity to plus infinity. Here it is in the positive side here. That is parallel to the x-axis at y is equal to minus 2, z is equal to 5. Here we have a line charge, such a line charge, and where you need to compute the value of electric field intensity in the part A. Here it is P in the bracket 1 2 3. So it can also be identified. So I just take the z axis, y axis, x axis